Hello everyone, this is chapter 8 in the textbook and it is process and the measurement system capability analysis. We have two parts in this chapter. In the first part, we are going to analyze the process capability, and in the second part, we are going to analyze the measurement system capability. And this measurement system capability also called as the gauge capability. Let's start with the first part, the process capability. In the process capability, we are trying to measure the inherent variability in the process. And to measure this variability, we can categorize the variability into two. The first variability we are considering is the instantaneous variability, and you can also think this instantaneous variability like a population variability. We can estimate the population variability, right? In the second variability, we are observing, we are monitoring the process, and we are trying to, compute the variability sample to sample. And that's why we can also think it as over time variability. Okay. So we have two kinds of variability, but we need to measure the process capability with which variability. We can use the first variability, the instantaneous variability, the population variability. That's why we can use the natural tolerance limits as a measurement of process capability. From the previous weeks, you already know that the natural tolerance limits are some deviation from the mean. And this is a usual natural tolerance limits are used in industry. It is 3. It is customary to choose 3, but you can change it. It is up to the process owner. And these natural tolerance limits defines the process capability. So we are here to measure. We are measuring the inherent variability in the process with the natural tolerance limits. Okay. And by the way, do not mix up things. Okay. The control limits, the natural tolerance limits, and specification limits are different things. They are like complementary things. They are related to each other, but they are different things. In the control limits, for example, what are we doing? We are taking some samples from the process, and we are trying to measure the variability sample to sample, and we are setting our limits by the sample data. Okay, in the natural tolerance limits, we are not taking different samples from the process. Maybe for estimation purposes, we are taking just one sample, and in the case of knowing the standard, the norm, the true value of mean and the standard deviation, we are not taking any sample at all. All right. So in the specification limits, we do not have any statistics. We are not measuring things. We are not computing things. The specification limits are determined externally, maybe by the engineering department, maybe the managerial side. They are determined externally. And to how can we analyze the process capability? We can analyze the process capability without regard to specifications on the quality characteristics. The process capability is not related to specification limits. Okay, the specification limits are external things. Process capability is another thing. Process capability is just measuring the inherent variability in the process. Okay, so we can estimate the process capability over the process data. And we can use the process capability in different purposes. For example, we can use process capability for selection, competing suppliers. And maybe we can choose the best one with regard to process capability ratio values of the suppliers. And also we can use process capability, for example, for the reducing the variability in the manufacturing process. We can compute the process capability, and if it's high, the process capability high in the limits, we can reduce the variability, so we can reduce the variance, the spread in the process capability, for example. Okay, so also there are different purposes also, you can read it here. And what is poor process capability then? How can we determine a process capability as poor or bad? There are some reasons for that. For example, in the second figure, in the middle figure here, let's suppose that the variance, the standard deviation value in the middle process capability is much more than the first one and the third one, for example. Here, because the spread is much more than the ideal one, for example, ideal one is here, ideal one is here, we can say that when the spread is high, the variance high, variability is high, the process capability is poor, because we are gonna get much more non-conforming products from this process because the high variability. So high variability is bad for us, high variability is bad for process capability. If we want to improve the process capability, we need to decrease the variability, we need to decrease the spread. And the first case, another reason for the poor process capability, we can observe here the mean of the process is shifted from the midpoint of the specification limits. So in the ideal case, the mean of the process must be in the middle point of the specification range. But here, the process center is off the midpoint of the specification limits. So when this is the case, also we are producing much more non-conforming products, because this area will be much more than the ideal one. So we are gonna get much more non-conforming products. So we do not want this, and this is the poor process capability. So in the ideal case, in the ideal process capability, the process mean would be in the midpoint of the specification limits, and the variability should be lower. Then, if we achieve this, if variability is low and the process center is in the midpoint of the specification limit, it means that we are not gonna get so much non-conforming products. We are gonna get little amount of non-conforming products, and which is good thing for us, right? Okay, so maybe here, for example, we are going to talk about it later, but let me emphasize this here. These are the specification limits, okay? These are not natural tolerance limits. Let's say these points are the natural tolerance limits. The end point of the blue curve is the natural tolerance limits, okay? And when this is the case, let's see here, for example, let's suppose that the lower natural tolerance limit is here, okay? And let's say that the lower natural tolerance limit is here, for example. And the upper, maybe it is bad writing because I'm using the trackpad, sorry about that. Let's suppose that this is the lower natural tolerance limits, and let's say this is the upper natural tolerance limits. And when the process quality is good, is better, the natural tolerance limits will be in the specification range, like that. But when the process quality is poor, the natural tolerance limits will outside of the specification limits, and this will cause loss of non-conforming products. Okay, this is the natural tolerance limits in this example, and this is the upper natural tolerance limits. Okay, etc. And here, maybe the lower natural tolerance limits is in the specification range, but here we are getting, exceeding upper natural tolerance limits, and it will exceed the specifications. That's why this is an example for poor process capability. Okay. So how can we analyze process capability then? How can we determine the process capability then? How can we say that this is good process capability and this is bad process capability? How can we quantize them? So we can use different techniques and tools for that. These are the tools, the histogram we can use, probability plotting maybe, and the control charts we are using for the monitoring purposes of the process. Also, we can use control charts as computing the process capability or analyzing the process capability. Or we can use designed experiments to determine and analyze the process capability. Let's start off with the histogram. Histogram tool, you are familiar with this tool. We are using histogram to make things visual, and when we want to see the distribution of the data, right? So if we use histogram, we can visualize the process data, the quality characteristics data. And for example, we can determine that the quality characteristics data is normal, because in the first thing, when we make a process capability, we assume that the quality characteristics in normal distribution. This is an assumption, but when we get data, when we encounter real situation, real data, we need to check the normality of the quality characteristics, normality of the data. So here, for example, these are the data we have, and when we make an histogram over this data, we see that the histogram seems normal. Okay, so it passed this test at least. So we can also compute the sample mean, right? And this is the number we get as sample mean, and this is the sample standard deviation. We do not know the true value of the standard value of the standard deviation, so we can use this sample standard deviation in our natural tolerance limits, in our process capability analysis. Okay, so the process capability can be defined or can be estimated like that. X bar, upper and lower side, we are taking the 3 sigma, 3 standard deviation value. So this is the process capability computation for this example. And from this, limits, from this capability values, okay, this is one way for the analyzing the process capability. So before passing to the probability plotting, maybe also I need to talk about some issues with the histogram using. So when we make a process capability analysis, we need to consider the machines we are using in this process. If we are using identical machines in the process, or identical heads, for example, in the CNC machines, for example, I'm just making an example here. If the machines are identical, so we can take an representative machines and then use for the analysis. But if we use different kinds of machines, non-identical machines, we cannot choose randomly a machine. All right, because there will be some machine variability in the process. So maybe we want to isolate this variability, so to compute the process capability just for the finding out the inherent variability in the process. So maybe we can calculate different process capability values for different machine kinds, okay? And this is also valid for the operator, for example. If operators are having the same performance, maybe we can choose a representative operator then use it, okay? But also, if we want to estimate the operator variability, we can select a random from the population of the operator, then we can put it in the analysis, so we can also see the effect of the operator variability in the process capability. So probability plotting is another alternative to the histogram to make analysis on the process capability. And we can determine the shape, the center, and the spread of the distribution of the quality characteristics by drawing the probability plots. It has some advantage over the histogram. For probability plotting, we do not need large sample, okay? Maybe a small sample can be adequate for the probability plotting. And for example, here we have some data, okay? And when we have data, we are ranking them first. We are ranking the data. Then we are calculating the cumulative frequency for each data point. Then finally, we can plot our probability plot. If the data points are, oscillating over the straight line and there is no significant deviation from the straight line, we can say that the data is in normal distribution. And when we look at this example plot, this particular plot, we can say that, yes, the data is in normal distribution. And we can use probability plots for estimation of the sample average and the sample variance. For the sample average, we can use the 50th percentile. Okay. So an obvious disadvantage of probability plotting is that it is not an objective procedure. It is subjective. Maybe in some cases, in some occasions, I call it as normal. The other one can call it as non-normal. Okay, it's not objective procedure. So we can try the goodness of fit tests for this input data. You are going to remember we were making some goodness of fit test to find the distribution of the data we have, right, in the simulation course. And it is like that when we get some data from the process, when we get some data, the measurements on the quality characteristics of the product over the process, we can, make some goodness of fit tests on this data and we can determine the distribution of the data. We are seeking here to find the normal distribution in the data, and we can use the goodness of fit tests like Shapiro-Wilk test or Kolmogorov-Smirnov test or Anderson-Darling test, etc. Then find the distribution and the parameters of the distribution, potential distribution or candidate distributions. So finally, let's talk about the process capability ratios. It is frequently convenient to have simple, a quantitative way to express the process capability. Okay. For this purpose, we can use the process capability ratio. What is process capability ratio? Process capability ratio is that we are dividing the specification range over the 6 sigma. And 6 sigma here, the sigma level is 6 because we are taking the 3 sigma from the upper side and 3 sigma from the lower side. So it is the deviation range is here in total is 6 sigma, but it can change. I'm saying it again and again, but it can change. It's up to the process owner. And these are the specification limits are determined over the product. Okay, and so we are here using the specification limits, but the specification limits are set. Okay, they are not random, they are determined. They are not statistics, they are determined. Okay, but here the sigma is here the deviation in the process, inherent variability in the process, and we are trying to analyze this variability by looking at the process cavity ratio. Okay, so when the process cavity ratio is big, is large, it is good for us because it means that the variability is reduced. It's not that much. But when the process cavity ratio, this CP value is lower, it is when it's small, it means that variability is high and it is bad. So the process cavity is bad. It is showing a poor performance. We need to improve it if the process cavity ratio is small. All right. So in practical, application, the process standard deviation here is almost unknown. So we need to estimate it. For estimating it, we can use the sample standard deviation as, or if we are using the control charts, the quality control charts, like X bar R control charts for the variable control charts, we can also use R range, R average, R range, average of R over D2 value. You can remember from the chapter 6, this is the estimation on the standard deviation, right? And we were dividing the average of R to D2 to make adjustment and make the sample variance estimation unbiased. Okay, this is like an adjustment factor here, D2 value. So we can use average of R over D2 value as sample standard deviation, the estimation of the standard deviation, if we are also using the control charts. Actually, in the process capability studies, one of the assumptions we are making, the process is statistical control, because we need to assume that thing, the statistically control processes, because otherwise the process cavity ratio calculations do not mean anything. Okay, if the process is not in control, we are just wasting time and effort to find the process cavity and making some analysis on the process cavity. The first step must be make the process is in statistical control, then maybe we can make analysis on the process capability. Okay, let's proceed. I'm just spending so much time in this details. Sorry. So this standard deviation is a parameter, and when we know the exact value of it, we can use it. But if we do not know it, we need to estimate it. So this is the estimation of the process capability, because this is the statistics for the parameter. Okay, so there's an example here. Let's say the upper specification limit is 1 and the lower specification limit is 2. And the standard deviation estimation, we can use average R over D2 because we are using the R chart in the example. And this is the numbers we get. By the way, you can check the example in the chapter 6. First example in the chapter 6. And this is the process cavity ratio calculation. It is here. Here in that example, we assume that the data is in normal distribution. So we can use the cumulative normal distribution table, and then we can find that in the process, we estimate that, we expect that in a million production, we are going to get 350 defective parts. How can we find this value? We are going to remember from the previous weeks, by these parameters, sample average and the sample standard deviation, we can estimate the number of non-conforming products by looking at the specification limits. Then we can calculate them. Okay, so check the chapter 6 and the example, and you can see the calculations. So a practical interpretation of the process capability ratio, we can use the percentages. And in this percentage data, we are gonna find the cover of the process capability, the natural tolerance limit in the specification range. So we are gonna use this formulation. For example, when we plug the last example's process capability here, and it will give us a number like 83. And we can interpret this 83 like this. The process uses 83% of specification band. So it is when it is lower than 100, it is good for us because we are not using specification range as much as bad occasions. In bad occasions, we are using specification range band, and we are also exceeding the specification range. So we are producing lots of non-conforming products. So it is good for us. We do not exceed the specification range, and it is lower than 100. Okay. So it means also the variability in our process is low. Okay. We do not exceed the specification range. Also, we want, maybe in some occasions, we want to calculate the one-sided process capability ratio. Maybe we have just one-sided specification limit, so we can use the one-sided process capability ratio. Or we want to compute it for the purpose of analysis, okay? And we can use these one-sided PCRs for the another alternative for the process capability ratio computation. We're gonna see a few minutes later. So the process in upper-sided process capability ratio, we are just using the upper specification limit, and we are extracting the mean of the process from the upper specification limits and dividing it into the 3 sigma level. And for the lower specification, process capability ratio, we are just using the lower specification limit, and we are extracting this limit from the process mean. When we do not know the true value of the mean and the standard deviation, we can use the estimations, and we do not know them. Okay, so interpretation of the process capability ratio. So here we have a table here. It's like a shortcut calculations. There are some levels of process capability ratio. Okay, it's just from the 0.25 to the 2, and these are the shortcut calculations for this process capability ratio. For example, if the process capability ratio is 1, so the specification band, specification range, just align with the natural tolerance limits. In this situation, we expect that in the one-sided specifications, if we are just using the one-sided specifications, in upper or in lower side, we expect that in per million production, we are gonna get 1,350 defective parts. In the two-sided, it is just the 2 times of this data, and it is 2,700 defectives per million production when the process quality ratio is 1. When it increases, the defective part fraction decreases, right? Because the variability is decreasing and the process quality ratio is increasing, and we are not exceeding the specification as much as in the lower process quality ratio processes. But there are some preconditions to use these shortcut formulations or the direct normal probability distribution calculations. First assumption, the quality characteristics must be normal distribution. and the process must be in statistical control. Okay. And in the case of two-sided specifications, the process mean must be centered between the lower and the upper specification limits. So if these are the specification limits, the process mean must be in the midpoint of this specification range. This is an assumption for using this kind of table. Okay. And also we can calculate our defective number of non-conforming product fraction for ourselves. For example, when the sample average is that value and the standard deviation is that value, and let's see the lower specification is just 200, okay? And if we just use the one-sided specifications, if we do not deal with the, for example, upper specification limits in this example, we can calculate the process quality ratio for the lower side, and it is here. This is the mean estimation, the sample average, it's here. And this is the sample standard deviation estimation, it is here. So we calculate the process quality ratio in the lower side, and it is 0.67. Also, by this data, we can also calculate the fraction of non-conforming product in our process. So we convert the our data to our normal data to standard normal data, and it is lower specification limits. We are considering the lower specification limit because we are trying to find the area here and then calculate the fraction of non-conforming product, because when the quality characteristics measurements falls behind the lower specification limits for this example, they will be non-conforming products, right? So this is our data, the quantile we are considering here, and the mean also is estimated by the sample average, and the standard deviation is estimated by that value, okay? And this is our Z statistics value in the it is in standard normal distribution, and it is -2. In standard normal distribution, we are converting data just the standard normal distribution by this calculation, by this statistics value, and the mean is 0, right? Because it is standard normal distribution, and our quantile is here, -2. And if it's -2, we can estimate the falling behind the lower specification limits probabilities 2.28, okay? In the percentage, it is 2.28, sorry. In probability, it is 0.0228, right? Yes. And so if it's the percentage, when we multiply this percentage with the 1 million production, it says the number of defective non-conforming products is 22,800. Let's continue. So this table is for the minimum requirements for the process quality ratio in different occasions. For example, in the existing processes, the minimum requirement for the process quality ratio are given for the two-sided and the one-sided specifications. Here, this table is just a common common practice in industry, but it can change. Okay, so it's up to the decision maker here. All right, and new processes, we need to use higher process quality ratio in both cases, in two-sided and one-sided cases. And for the safety issues, we need to also use higher process quality ratios. In Six Sigma companies, the minimum requirement for the process quality ratio is 2, okay? And this is lower than the Six Sigma applications. Here, the process, here, for example, process quality ratio requirement is getting higher, right? Actually, it means that they're reducing the variability Okay, in safety issues, for example, we need to reduce the variability, then we can get higher process quality ratio, right? And about the CP again, the process quality ratio calculation, it does not take process centering into account because we are just using the specification limit data and the standard deviation data. We do not know where is the center of the process and what is this relation between the center of the process and the specification limits. So we can use another kind of formulation for this. It is CPK, and it is simply the one-sided process quality ratio for the specification limit nearest to the process average. And we are taking here the one-sided process quality ratio, which is the nearest to the process average. All right. So we are calculating the upper-sided process quality ratio and the lower-sided process quality ratio, and we are taking the minimum of them. So we are finding the one is nearest to the average of the process. Okay, and CP can be counted as potential capability of the process, but CPK is the actual capability of the process. Okay, here, why do we call them as like? Here, we can see that, for example, the CP and CPK is equal to each other because the process center is in the midpoint of the specification limits. But when the process mean is, off the midpoint of the specification limit, it is, for example, in the right side of the midpoint, process quality ratio is same because specification limits do not change and the standard deviation do not change. That's why process quality ratio is again 2. Okay, this is 2. The division of that range over that range is 2. And CPK is getting lower. It is 1.5. Why? Because the mean is getting closer to the upper specification limits. That's why the specification range in the upper side is reduced. That's why the CPK value is reduced. In the extreme case, CPK value is getting negative values because the mean exceeds the specification limit in the upper side. So it means that there will be lots of non-conforming product. Okay, there will be lots of non-conforming product. So it will be wise to use CPK instead of CP, or at least we need to use them. We need to use them together. Okay, so it's just an example here. Skipping it. So if they are equal, CP and CPK is equal, it means that process center is in the midpoint of the specification. If it's lower than the CP, the CPK is lower than the CP, it means that process is off center. About the normality of the process quality ratio, the assumption of normality is critical to the usual interpretation of these ratios, process quality ratio CP and CPK. Okay, but if we have non-normal data, we have some options. The first option, we can transform the non-normal data into normal data. For example, we can use reciprocal of the data. If it's in normal distribution, we can use it. And second option, we can extend the usual definition of the CP and the CPK to handle the non-normal data. For example, we can use the CPC. It's an alternative for the CP and CPK. You can check the textbook and the reference academic papers in the textbook, and you can find more information on the CPC. And the third option, we can modify the definitions of the process quality for general families of distribution, so we can directly use the quantiles, okay, for the process quality ratio. Here in usual CP calculation, we have 6 sigma here, but we can also convert this 6 sigma, just finding the probability limits in the distribution. Here, for example, these probability limits represent actually the 6 sigma limits. These are the quantiles, all right, the distribution of the data. So we can also talk about other types of process quality ratios like CPM and CPKM. There are lots of academic papers, and you can find these references in the textbook. If you are interested in the topic, you can read them about. You can check the calculations and computations of this process quality ratio, alternatives. But the textbook says that there is no significant evidence that these ratios, these new alternative ratios, are used to any significant extent in practice. Okay. So usually in industry, they use CP and the CPK, process quality ratios. And because we are using a random parameter in the process quality ratio, right? We need to construct confidence interval, and this will make the analysis of the process quality much more meaningful because there is randomness. So we have an error margin on these random parameters. Okay, from the probability course, you can remember the statistics chi-square is equal to the n minus 1 multiplies with the sample standard deviation square, the sample variance actually, and over the population variance. This is the statistics chi-square. And it is in the chi-square distribution, okay? And we can use this equation to find the confidence interval on the 1 over standard deviation, population standard deviation, okay? We are going to make some algebraic manipulation to convert it into the 2, this interval, right? In the right-hand side, we have chi-square alpha over 2, the degrees of freedom n minus 1, okay, in the right side. In the left side, we have chi-square 1 minus alpha over 2, because we are trying to find that area. Okay, that area will be this interval. That area, probability of that area is the 1 minus alpha, okay? And when we make the proper algebraic manipulations, it becomes this. And we are taking the constants in the process quality ratio and plug into this interval, all right? And this 1 minus 1 over standard deviation becomes CP, process quality ratio, because we multiplies the 1 over sigma with this 1 upper specification limit minus lower specification limits over 6. And we are also multiplying these terms in the right and the left side of the process quality ratio interval. And it will become this, okay? S is here, guys. It comes here, Then, because this is the estimation of process capability, we reduce the interval into that, okay? Process capability ratio confidence interval can be obtained from this, okay? And chi-square values can be found in the appendix in the textbook, okay? Let's continue then. For example, upper specification limit and lower specification limit is given here for an example, and the standard deviation is also given. And the question is asking, find a 95% confidence interval on the process coverage ratio. So let's plug the numbers into the formulations. This is the process coverage ratio estimation. Okay, we are using the sample standard deviation value here. Okay, and this is the process coverage ratio estimation. We want to construct the confidence interval in the 95%. So alpha will be 0.05 and alpha over 2 will be 0.025, right? And this is just plugging the numbers. And the process coverage interval, confidence interval occurs like this. But here, when we analyze this interval, in the lower side, process coverage ratio is okay, it is adequate, but in the right side, upper side, this probability ratio, process coverage ratio is very, very good. So there is a wide range, for the process coverage ratio values. So what is the reason for this? Maybe the reason is the small sample size. Here, the small sample size we are using, it's just 20, so it's a small sample size. So we know that the sample standard deviation is very sensitive to small to moderately sample sizes. So there is an option we can increase the sample size and construct the confidence interval again. And the other option we can use the R range over D2 sample standard deviation formulation rather than the sample standard deviation just as, because CP is only meaningful when the process is in statistical control. If the process is in statistical control, we use that formulation for the sample standard deviation. So if the process is in statistical control, in CP, process coverage ratio, instead of using S directly, we can use the average of R over D2 value. Okay. Let's continue. And this is the CPK confidence interval. You can find the proof in the academic papers given in the textbook. Okay. This is just a computation of the confidence interval of the CPK. And this is just an example for this. The values are given. This is the estimation of the CPK. Okay. And we want to construct a confidence interval in 95%. You just plug in the numbers, okay? We are just using the numbers. Then plug in here. Then we come up with the interval, confidence interval for the CPK. It is also wide. Why? Because the small sample size, right? Sample size is also small here. This is wide, right? Because in the lower side, CPK says it is 0.88. In the upper side, it is 1.78. When the CPK is lower than 1, it is actually very bad for us. It means that we are producing lots of non-conforming products. But in the upper side, it says it is 1.78, but it's a good score for CPK. So there is a very huge range here. So we need to reduce it, and we need to be more careful about the limits on the confidence of the CPK. Okay. And also, if we use just directly the sample standard deviation, we can calculate the process performance indices. And it is invented because when the processes are not in statistical control, when they are out of statistical control, for example, automotive industry says that we can use the performance indices is PP here and the PPK here, and we can use the sample standard deviation directly in the process quality ratio formulations. But there is a huge opposition for using this kind of calculations with the sample standard deviation when the process is out of control. And some scholars say that if the process is not in control, if the process is not under the statistical control, you cannot use, the process quality ratio like this. Okay, you cannot use it because it's like what? It's like statistical terrorism. They use this term for using this kind of calculations when the process is out of control. Okay, because the first aim here must be to make the process is in statistical control. Then we can talk about the process quality ratio. Okay. Also, another tool we can analyze the process capability is the control charts. This is actually the primary tool for the process quality analysis. And we have an example here, example data here. We have 20 samples and each sample has 5 items in it. This is the grand sample average, and this is the range, average of range. Okay, so we calculate the estimation of the mean, the grand average, and this is the sample standard deviation estimation, average of R, the range, over D2, and it is that value. And specification limits are also given in here, in this example. It says specification limit in the lower side, it is 200. And that's why the lower side process quality ratio will become this, the mean minus lower specification limit over 3 sigma. And here we are using the estimations instead of mu and the standard sigma. Okay, here. And the lower sided process quality ratio is this, 0.64. It is not nearly to 1, at least, and it is not good for us. But when we look at the X-bar control chart and R control chart, they seem under control, right? They seem in statistical control, but the process quality ratio is not that good. So the process is in statistical control, but the poor process quality. So engineering management intervention is required for this process because operators cannot make anything at this point because the X-bar and R control charts are in statistical control. So operator cannot do anything about it. So here at this point, when we also calculate the process quality ratio with this in control charts, we can infer that we can make an interpretation like this. We need to take engineering or the management intervention to reduce the variability so we can increase the process quality ratio. And the last tool we can use for process quality analysis is designed experiments. What is design experiments? It's a systematic approach to varying the input controllable variables in the process and analyzing the effects of these process variables in the output. So we are going to make some arrangements, some experiments on these controllable inputs, to see the effect on the output of the process. Okay, so one of the major uses of the design experiments in isolating and estimating the sources of variability in the process. And when we isolate the variability in the process, the sources of the variability in the process, we can focus on these sources and we can reduce them so we can increase the process capability. Okay? That's why we are using design of experiments for the process capability analysis. Here there is an example. For example, consider a machine that fills bottles with a soft drink beverage like this. This is the process. Each machine has a large number of filling heads. These are the heads, filling heads, that must be independently adjusted. They must be independently adjusted. The quality characteristic measured is the syrup content. This is the syrup, okay? This is the syrup. And the syrup content measured in the degrees of Brix, okay? Brix is the measurement level. The syrup content of the finished product. There can be variation in the observed Brix. This is the variance on the Brix, on the syrup content, okay? Because of the machine variability, and this is the machine variability, this is the machine variance. Head variability, this is the head variance, and the analytical test variability, this is the analytical test variance, and the total variability over the observed Brix variability can be expressed like this. Brix variability, Brix variance is equal to machine variance plus head variance plus analytical test variance. And we can maybe, explain the variability in the Brix, explaining the variability in the syrup content with the variability in this controllable inputs. Okay? So if we find a significant variability over this, machine head or analytical test, we can focus on that and we can reduce the variability. So we can reduce the variability in the Brix, in the syrup content for this example. Okay. So an experiment can be designed involving sampling from several machines. For several machines, we are going to take samples. We're going to take samples from several heads. We are going to make several analysis to see the variability in the analytical test, if there is any, okay? And we are going to observe the variability in the Brix, in the syrup content. And when we look at the figures, the distribution spreads, machine variability is not that much, but head-to-head variability is much more than the machine variability. So we can make an inference like this. A substantial total variability occurs due to the head-to-head variability. Process can be improved by the reducing variability over the heads in the machines. So there is we can make some adjustment on the heads. Okay, so we can reduce the variability over the heads. Then we can reduce the variability in the syrup content. So we can increase the process capability ratio for the syrup content. Okay. So up to here, we have talked about the numerical data. But if we have attribute data, discrete data, what can we do about it? How can we, calculate the process capability and then improve it? For the process capability analysis in the attribute data, we have different kind of formulations, and DPU is the one of them, and DPU means the defects per unit statistics. Here we can measure the capability of the process on the attribute data by this formulation, DPU formulation, and it is total number of defects over total number of units. Here, be careful, it's not defective, it is defects. As you can remember from the previous weeks, one product can have several defects, but it is not necessarily to be defective. So these calculations can be used for the process capability analysis in the attribute data. We have also another kind of formulation. Here it is DPMO, and DPMO is the defect per million opportunities. Here we are dividing total number of defects into number of units multiplied with the number of opportunities. Here we did not take the units as whole. Instead of this, we calculate opportunities. Opportunities means the potential places, potential fields for the defects, and we multiplied these potential fields with the number of units, total number of units. Okay, so that was it for the part 1, and let's see you in the part 2.